Okay, thank you very much. It's a pleasure to be here. I'm going to be giving a tutorial on financial derivatives, and in particular on networks of financial derivatives and clearing these networks of financial derivatives. So for those of you who maybe are less familiar, financial derivative is a payable that becomes due when an event triggers it. So it is a contingent claim. And when we think about the payables at the level of a financial system, what emerges is a network. And this is a network that has potential impact on the entire economy. And we have had over a decade of research in this topic ever since the financial crisis. This particular tutorial is going to be a joint work with Amini, but in general, there has been an explosion of research on financial derivatives and in particular from the system viewpoint. So let me share my screen. All right. So this has been motivated by events like the fall of Lehman Brothers, and following that, in particular, a notorious event that was the almost collapse of AIG. So AIG was a player in credit derivatives. This was part of the over 400 trillion notional over-the-counter market. So financial derivatives that do not go through an exchange, but are largely, you can think about them as peer-to-peer, so counterparty to counterparty, and they were quite unregulated. So so AIG was a huge player in credit default swaps. So those are payables that come due upon a credit event, such as a bankruptcy. And it was the case of the bankruptcy of Lehman Brothers. And had it not been bailed out by the government, probably AIG would have become bankrupt as well. So after the financial crisis, there were a comprehensive overhaul of financial markets, and this came in the form of the Dodd-Frank Act of 2010, and in particular the US Commodity and Futures Trading Commission, so CFTC, which was the regulator for financial derivatives, has been authorized to regulate also the over-the-counter market in order to lower the risk. And one of the pillars for this, for how risk is supposed to be reduced, is the introduction of central counterparty clearing. This means that instead of having over-the-counter payables, instead of having over-the-counter flows between any two parties, what will happen is that there is a centralized clearinghouse that is going to process all these payments, and that is of course going to reduce the interconnectedness in the market, because not all the parties are going to be connected to each other, but is going to introduce this new node in financial markets, which is the clearinghouse itself. And of course, a lot of research has been following this mandatory centralized clearing in order to understand how to make clearinghouses more robust. So what is a clearinghouse? A clearinghouse is going to modify the structure of the market. So if you have before the clearing an obligation, say from 1 to 2, and this obligation is of a certain amount X, which is not necessarily deterministic, so this can be a contingent claim. Well, this is going to be replaced, or what we call novation. It is going to be replaced by two contracts, one between the first counterparty and the CCP, and the second one between the CCP and the second counterparty. So this will happen for every contract. And one of the effects that this is going to have, for example, if you have a cycle in the network, so if we look at this example, 1 owes to 2 and 2 owes to 3 and 3 owes back to 1, when each of these contracts is going to be replaced by the contract to the CCP and from the CCP, and we aggregate all of this over the entire over this entire network of contracts, what will happen is that we are going to have a star network, and the star network, a node 2 here is going to go to the CCP, and CCP is going to own node 1 and node 3. Why is that? Well, node 2 here, note, it is a net payer to the network. So it receives 50 from the network and it pays 100 to the network. And when we're going to net all of this, it turns out that, of course, node 2 is a net payer to the network. And then, of course, node 3 is a net receiver. And node 1 is also a net receiver, having more receivables than payables. So the first observation is that the network becomes a star network. So this is something in terms of the topology of the network. But what is equally important is the fact that the payables, so what each node must pay, so for example, 2 here must pay 100, regardless of whether it receives or not. Well, here the payables are reduced, right? Because we do this netting. And when we do the netting over the entire network, this is called multilateral netting. So this is one of the functions of the clearinghouse. So the clearinghouse replaces much of the bilateral trading. It reduced interconnectedness and eliminates cycles. And the initial network becomes a star network. The payables are reduced, as I said, and this is something that has been studied in one of the first papers on the impact of a clearinghouse. So the CCP is going to change the shortfall profile across the network. So more nodes are potentially impacted by the clearinghouse. And I like in particular this quote from Janet Yellen. So the other side of the coin, so the other side from reducing interconnectedness and reducing the payables in the network is, of course, the fact that we introduce a single point of failure in the network. So it is then critical that the clearinghouse is well managed and well regulated. And you would think that after 10 years, it is clear how to manage clearinghouses, it is clear how to capitalize them. But in fact, this is far from the truth, and much more research is needed to address the matter. In fact, this is a very contentious issue, and I'm going to be talking later more about this, but the whole capital structure of the clearinghouse, basically who is paying first and whose capital is going to absorb the losses first. These are matters that remain debatable. And so this brings me to the second point. So the second technique, the second network service that could decrease risk across the network is another, is also a network service. So this is called portfolio compression. Portfolio compression goes into the initial network, and the goal is to decrease the payables on a cycle. So if we target directly the cycles, you see here that you have from node 1 to node 2 and to node 3 you have these payables. And when we do portfolio compression, then what we are going to seek is the smallest liability on a cycle, and then decrease all liabilities on the cycle by the smallest liability, and we obtain something like this where the cycle is actually broken. And not only the cycle is broken, but also similarly to the case with the centralized counterparties, the total payables are of course lower because we have decreased them by the smallest liability. And a few words about the literature, and there has been, so it's just a very small number of papers that has addressed clearinghouse, and there are much more works that address in general systemic risk and financial networks, but I will not enter those details here. So all of this is in the written tutorial. So I would like to emphasize a few viewpoints. So Duffy and Ju, they show that when we introduce a clearinghouse, there is of course a trade-off. So the clearinghouse is going to do the multilateral netting, but one should also acknowledge that things are a little bit more complicated, because there isn't just one network of financial derivatives. Financial derivatives can be separated across classes. So maybe the trigger are credit events. The other ones, they are interest rate derivatives, because the triggers are interest rate events. So when we introduce clearinghouses may be specialized for each asset, for each type of financial derivative. Whereas when in some original network where that is not centrally cleared, there could be the potential of bilateral, so each two counterparties netting across all these types of financial derivatives, so netting across asset classes in financial derivatives, known as, for example, an interest rate swap and a credit default swap, and thereby decreasing the maximum payable. And so there is a trade-off between this bilateral netting and the multilateral netting for each type of derivative, and they show that this is not trivial, and the clearinghouse could make things worse. In some of our work, we have looked at other viewpoints regarding clearinghouses. What happens if you choose a subset of payments to be centrally clear? So what if you don't let all the network to go through the clearinghouse? Also, what happens, is there a way to find a capitalization of the clearinghouse? Is there a way by which the members of the clearinghouse, so meaning the financial institutions that are going to clear through that clearinghouse, is there a way for them to fairly participate to the capitalization of the clearinghouse? And this comes in the form of default fund contributions. Those become part of the capitalization of the clearinghouse that is supposed to absorb losses that come from the member itself, but also mutualized losses. So losses that come from everybody who is a member of the clearinghouse. There's also very nice work by Glasserman and co-authors on competing clearinghouses, and on portfolio compression. Recent works have turned their attention to this additional network services, and what they find is that these network services are going to change the seniority structure in the network. So those are points that have been only recently made in the literature, and part of this tutorial is to emphasize these points. So what we are going to be using is a very convenient framework, Eisenberg-Noe, which in fact it is very similar to thinking about cash flows in the same way as we are thinking in operations research about network flows. So we try to find an equilibrium in the financial network that specifies how much each node is able to pay, given what other nodes are able to pay to that node, and of course kept at the due payables by that node. So this is a clearing fixed point. So this is a network fixed point, and this has been very successful, in particular in the operations research community, because there's an optimization viewpoint. So computing the fixed point, it turns out that can be done via linear programming. And I also recommend reviewing one of the 2018 Informs tutorial by Birch and co-authors. So Now, what we bring new in this tutorial is the fact that we can use this very convenient framework in order to assess the effect of various network services in financial derivatives and the effects on external asset prices and on the seniority of claims. And this is particularly important because, in general, we are interested on the impact of the clearing the financial network on the outside economy. So let me show you what clearing a financial network in the Eisenberg-Noe is about. So financial contracts, as I said, are random payments that come due in the case of an extreme scenario, omega. So our setup is going to be the following. We're going to have M banks, and each bank is going to be endowed with gamma I units of cash and yi units of this external asset. And this is very important, the presence of this external asset. Those are all kinds of other projects that the financial institutions are involved in. And there are 3 dates. So this is a variation of the classical Eisenberg-Noe framework. And this is adapted to the financial derivative setup. So there are 3 dates. At time 0, we enter the contracts, and the payments are realized at time 1. So this means that the trigger of the financial contracts comes at time 1. And there are LIJ, those are payments that are due from bank I to bank J, to the other banks. There are receivables that bank I, so those are called RI, and those come from end users, so from the outside of the financial system, if you want, or and there are payments, DI, that go to outside the financial system. So those are also to end users. And one can ask, okay, what are the end users? So the end users are all kind of participants in the global economy who are looking to use financial services in order to hedge their own risk. So financial derivatives are a tool essentially to hedge risk. So we can assume that in the original network, the payments to the end users are senior with respect to interbank payments. And there is this external asset that will play an important role. And one unit of this asset will realize the value V at time 2. The main point that we want to make is that in clearing, so in determining the payments on the financial derivatives at time 1, we can have, of course, an impact on this external asset. Think about a bank or a financial institution who has to pay a huge amount of money, and they don't have cash at hand, so they have to liquidate this external asset. This will destabilize markets. And in fact, this has been one of the most important triggers of the regulations of over-the-counter derivatives. So this the creation of instability in financial markets. What does it mean, instability? Well, one side of this instability could be the instability of prices of external assets when we try to make the payments related to financial derivatives. The mathematical definition of an equilibrium in the Eisenberg-Noe is as follows. What we have here, we start with a shock epsilon I, and we assume that the bank I receives from its customers not its entire due receivables, but there will be this shock epsilon I. So then Li star is going to be the equilibrium payment. So what the bank is able to pay, taking into account that it may not receive its own due receivables in full. So it's going to pay at maximum what it owes to the others, and it's going to pay if it cannot reach this maximum, then it is going to pay the it is going to pay what it holds in assets. And what it holds in assets are this gamma I, so that is its cash holdings, plus what it receives, minus what it has to pay to its to end users, because these are senior to the payments to the other banks, plus what it receives from the other banks, and plus YIP. That is exactly this external asset, and it is evaluated at a market price P that is realized at time one. And the notes that default are those that are unable to meet their liabilities in full. So how do we share? So this LI is the total payables of Bank I. How does it get shared across the debtors of Bank I? Well, it can be shared proportionally, but there may also be some default losses. And there's a paper by Rogers and Berard of 2012 that deals with default losses. In general, there may be also multiple fixed point, and it is common practice in the literature to choose the largest fixed point. In general, those fixed points form a lattice, and the largest fixed point, it has an economic meaning, because it is it's more like starting with we first assume that we get everything in full, and then we update what we actually are able to pay, and then because we pay less, then my neighbor will pay also less, and then we update until we reach a fixed point. So from L star, from the payments in equilibrium, we can obtain the actual payments to the end users, the liquidations in equilibrium for a given price P, the terminal net worth of a bank in equilibrium, the surplus in equilibrium, and the shortfall in equilibrium. And one important identity is about the aggregate surplus in the banking system, and it goes like this. It says that if I look at the capital surplus of all banks plus what has been paid in equilibrium to the outside, well, this is going to be equal to the entire to the sum of all assets in the financial system. And those assets are the initial cash. Those assets are what was received, what came to the financial system from end users, plus the external asset valued at its valued at its what is supposed to be at its end payable V, and of course some of this external asset has been destroyed, has been liquidated at time one, and this part that has been liquidated is ZI. So this ZI will be liquidated as a lower price, so the difference between V and P will come as a loss. And in fact, if there's no asset that is liquidated, then as you can see, there is this value of the asset is the same before clearing and after clearing of the financial derivatives. So the impact of clearing financial derivatives on the overall value of the total assets in the financial system comes only through this part over here, which is the amount that is liquidated in the system. So it is these liquidations, I remind you, that drove regulators to create this important Dodd-Frank Act, this bill that basically mandates that financial derivatives are centrally cleared in order to stabilize the market. And stability means in particular that there is no disorderly liquidation in the market. So a disorderly liquidation would mean precisely liquidating because all of a sudden there are these large contingent claims coming from derivatives that become due. So now a general equilibrium is an equilibrium in which we look at the same time at the price of the assets and the equilibrium payments among financial firms. So to give an example, let's assume that we have two banks. So the first bank holds 1 unit of this external asset, and it has a liability to the second bank of 100. And now, because the second bank has no liabilities, it will never need to liquidate anything. It just, it's a net receiver. So it is bank one that needs to liquidate. But in this very simple example, the only buyer of the asset is bank two itself. So equilibrium can in fact only occur if bank two is willing to hold 1 unit of the risky asset. And this may not be the case because the value that this that this risky asset will bring in period two is in fact a random value, right? It really depends on the risk aversion of bank two, whether it wants to hold this asset or not. So in the following, we're going to make an assumption on how banks are what is the utility of the banks from holding such asset, and we assume that we have an exponential utility. It's a very convenient form, and rho I is the risk aversion coefficient of bank I, and this fundamental value of the risk asset is normally distributed, and there's some mu. This is the average, and sigma squared, that's the variation. That's the variance, and so our first theorem says that gives a condition for which an equilibrium price can be found at time one for the risky asset. And so white dot here, it is the sum of all assets. This is the number of units of the risky asset that we have in the system. And these units can move around, can be liquidated, but their number is of course going to stay the same. So they can be, they will stay in the system. So the condition is that the average of the risky asset divided by its variance, so this is a Sharpe ratio, it is sufficiently high in relation to the risk aversion of in relation to the average risk aversion of the banks that are liquid, even if the price that it's fetched by the asset is zero. So if we have this, then we have a chance. So this is a sufficient condition. It's not a necessary condition. The sufficient condition to have a unique price. And a unique price is such that y star, so that is how much each bank wishes to hold in equilibrium, for the price p star is the same as the total amount of the asset in the system. So bottom line is that if we look at bank two's unconstrained optimization, so in the previous example, is such that even at a price zero, it is not willing to hold 1 unit of the stock. So if the price was zero and the bank had zero, had no constraints of wealth, then what it would wish under an exponential utility to hold, it is mu divided by sigma squared times the risk aversion coefficient. This is how many units of the asset it was willing to hold. And recall, it is supposed to hold 1 unit of the asset. So if that is smaller than 1, then there is no equilibrium. Okay, if this, on the other hand, if this is larger than 1, so if the bank is willing to hold more than 1, then the asset will be transferred from bank 1 to bank 2, and there is a unique price p star for which bank 2 is willing to hold exactly 1 unit of the asset. And in this equilibrium, the payable between 1 and 2 is going to be Li star is equal to p star. So what is the impact on prices when we introduce a clearinghouse? And this comes again from the observation that clearinghouses have been mandated especially to reduce such price instability. And indeed, what our theory shows is that if we look at full multilateral clearing, so if everything, if all liabilities in the network are being are being cleared through the clearinghouse, then the equilibrium price will satisfy that P star is greater than P star hat. That would be the equilibrium with the clearinghouse is going to be greater than P star. Now, other considerations when we introduce a clearinghouse are not just about the price. It is also about the counterparty risk, because remember, a clearinghouse is going to introduce a single point of failure. So the clearinghouse is also going to be equipped with a capital structure. So there is capital that is transferred from the members of the CCP to the CCP, and so this is called the waterfall procedure. What happens in case there are large losses? How are they going to be absorbed? So in case a CCP member is unable to pay, then the first layer to absorb the shortfall is the member's contribution to a default fund. And of course, in reality, there's more. There's an initial margin fund, and this is very, very, very large. So we can think about here as the loss after we have taken into account also the margin fund contribution. So now it goes into the CCP default fund, and then there is additional layer of protection that comes from the CCP external shareholder. So this is the CCP equity. And if the shortfall is very large, it is also going to be absorbed by the pooled default fund. So this is the default fund of everybody else who has not necessarily suffered losses. That is going to create loss mutualization. And there is still contention about how big this external contribution of the CCP should be. There is also another contention point, how maybe this part here should absorb losses after this part here, and of course this would have implication on the size of this contribution. So nothing is really nothing is really given in terms of what is the optimal capitalization of clearinghouses. So all these are subject to research and subject to debate. So from a mathematical standpoint, how can we model a clearinghouse? We can label a clearinghouse as node I is equal to 0. We assume that all payments are cleared through the CCP. We have a star-shaped network, and we have a proportionality rule, which says that CCP payments have equal seniority. And interbank clearing equilibrium can be directly computed in this case, and because there is no fixed point problem. Now the CCP is going to be endowed with its own capital, with a default fund, and when the default fund is going to be smaller than the cash of the bank I at time t is equal to 0. So from a systemic viewpoint, what we desire is to have as much loss mutualization as possible. So we need to incentivize members to put as much as possible in the default fund, because the default fund is essentially an insurance pool. So what we have suggested in our research is that guarantee funds can be netted against extreme payable. So this means if there is an extreme payable, then we can treat these guarantee funds or default funds as upfront payments. Of course, this is not for the usual liability or for the daily margining or for a small. This would be the liabilities under a extreme event that would be. And the idea would be that we would not need to have additional liquidations, right? Because if you have to have a large payables, it's very unlikely that one has the cash. So they will have to liquidate part of the asset, thereby creating a lot of instability. So if we allow that, we can use the already posted funds as and net against extreme payments, then additional liquidations are limited. So what does this mean? It means that that banks have more incentives to put these large funds in the default fund in the first place, because right now the default funds are quite small, and of course banks would view them mostly as capital that can be mutualized, so to absorb the losses of somebody else. So there is a natural disincentive to post a large default fund contribution. Now, if they are able to use this default fund in a way that minimizes their losses, minimizes the liquidation losses, then they would be able to pay more than under different rules. So what we have shown is that this idea of hybrid default funds, so the default funds that can be netted against extreme liabilities, that it leads to smaller liquidation losses, and there can be Pareto improving policies, and this can be achieved via solutions to Nash bargaining games. So to show you how it looks, here we plot the default fund contribution, and here we plot the systemic risk. So this is the risk to end users or to society as a function of the contribution of each bank. So in this black dotted part, banks cannot net with their liability. So there will be for equal G, so for equal contribution, of course, there will be more resources that are available in this part, because there are additional liquidations in this one. The banks, the systemic risk is going to be reduced for lower contributions of G in the non-netted case with respect to the netted case. However, when we look at the incentives of the banks will have lower, will break even much faster in terms of their equity. So if you look at the bank utility in terms of the expected capital of the bank, they do not want to put a guarantee fund contribution or make a guarantee fund contribution above this value in the non-netted case, and they would be willing, if we net, to put a much higher guarantee fund contribution. And for the clearinghouse wants, of course, to have as high expected capital as possible, and you see it will accept a guarantee fund contribution larger than this value in the non-netted case, and larger than this value in the netted case. And of course, the real point is whether we can find an intersection of all these intervals. And it turns out that if we look at the non-netted case, the fact that banks are reluctant to put as much capital as necessary, as much guarantee fund as necessary, then we cannot find a solution that improves the utility of everybody involved, and at the same time reduces systemic risk. So what I also want to emphasize that here it is those are graphs for different G's, right? So for the same G, so assuming the same G. When we're looking at a Nash bargaining equilibrium, of course, the implication of this entire shape is that in the netted case, we can find a G that makes everybody better off, whereas in a non-netted case, we cannot even find such G, right? So let me now go to the last point of my lecture, which is about the effects on end users. So assuming that in the initial network we have that end users are senior to the banks across the network, what we can observe is that when we introduce central clearing, they will de facto become junior with respect to the nodes in the netted system. And so here in this picture, what you have is that, so here, when I write 40 out of 50, what it means is that it owes 50 and it's going to be able to pay 40 out of the 50. 2 has has a buffer of 60 cash buffer, and it's able to pay 100 out of 100, and so on. So 3 in particular, who has a debt to end users, is going to receive this 100 from 2, and it's going to pay 60 to end users because they are senior, and then the remaining 40 to node 1. And when I do a CCP, the CCP is going to net this thing. So in fact, node 2 is going to owe only 50 to the CCP, and then the CCP is going to distribute that to node 1 and node 3. So in fact, whereas here node 1 was losing in the seniority, so it was because of the seniority and having reduced seniority with respect to end users, it was bearing a certain loss. Here it is the end users who are bearing the loss in the system, and the loss comes from the fact that node 3, which has 0 cash, receives 30 here and is unable to pay the full 60 to the end users. You see that in this example, introducing a clearinghouse is going to make everybody in the clearing arrangement more senior to everybody who is left outside the clearing arrangement. And in portfolio compression, it is very similar, and it's a situation that has been pointed out by other researchers as well. And all payments on the cycle, they are decreased by the smallest payment. So I take the exact same example as before. So the smallest payment here is going to be 50. And so then in this portfolio compression game, we are going to have that 2 owes 50 to 3, and 3 owes 20 to 1, and then 3 owes 60 to the end users. And well, the seniority, however, is going to be kept. So if you want to think about them in terms of network capacities, when we say here that the payable was 100, this you can think about as the capacity on a certain link. So you have a capacity, and then you want to see what is the flow that goes on that link. And now portfolio compression, it is essentially decreasing capacity. So then if you decrease capacity on the link that goes to node 3, then then the flow can be at most that capacity. So only a flow of 50 is going to reach 3, whereas 3 owes 60 to the end user, so that, you know, in some sense this capacity is not going to be filled, and that's bad. So this idea of having fulfilling the obligation to end users means that you would want that on the edges to end users, you would want to have a flow that is equal to the full capacity of the link, and anything less than that is going to imply a loss to the end users. Yeah, and the portfolio of some payments becoming more senior due to partial multilateral netting has been pointed out in various works. But the additional point that I want to make is that conditional on the compressed network being harmful, the novation to this clearinghouse can be even worse. And let me show this via an example. Let us look again at this example. This would be the clearing. This would be the compressed network. So the compressed network is as before, and this is going to go to a clearinghouse. And in fact, novating a compressed network, so novating passing to a clearinghouse a network from which I have already removed the smallest payable on the cycles, is going to lead to the same network as novating the initial network. So I hope that this is clear, that you know, so putting to a clearinghouse this portfolio compressed network is the same as putting to the clearinghouse actually the original network. So this cleared network is the same, right? So now, why is this helping us? It is helping us because recall that in a portfolio compression, so if we just do portfolio compression, the seniority between the seniority of the link of between 3 and n users remained higher than the seniority of the link between 3 and 1. Okay, so now if I go to a clearinghouse, then this would be equivalent to having switched to a seniority situation where node 1 is senior, so the link between 3 and 1 is senior with respect to the link between 3 and the end users. And here I plotted the senior links are the ones in red. Recall that in the portfolio compression case, the link in red was this one, right? So it was going from 2 to 3 to end users, and having the clearinghouse simply means that this here no longer red, so the one that becomes red is this one. Okay, so this is exactly equivalent. So this change in seniority, it is exactly what the clearinghouse is doing if you look at the payables. So so with this, I bring these various points that have received a bit less attention in the literature, and then to recall what we have seen, contingent claims can have an impact on asset prices. So in particular, you can have that an equilibrium asset price may not exist. This is exactly, but this would be a mathematical interpretation of asset market becoming unstable, and this has been the rationale for introducing clearinghouses. And under conditions that a general equilibrium exists, then full multilateral netting does indeed lead to higher asset prices and aggregate surplus. So if indeed we are under the condition that the risk aversion, so there's this condition of the risk aversion being sufficiently low with respect to the Sharpe ratio of the external asset, then we can have an equilibrium, and having that equilibrium and then the price that is reached under that equilibrium is higher when we clear the entire network. And the last point that I made was that both centralized clearing and portfolio compression can have unintended consequences on end users and parts of the network that are left outside the multilateral netting agreement. In particular, there is the loss of seniority. And moreover, clearinghouses can even be worse from that perspective. So there are open questions, and I hope that it is clear that these problems are very similar to network flow problems. In fact, you can always use the analogy that what is due, that is the capacity. You want to be as high to the capacity. The difference between the flow and the capacity, that is the loss or a shortfall. And then there is this whole notion of seniority. It's almost that you flow doesn't go on the network regardless of the order. There is this seniority, so there is an order in which flow will go on different edges. So this is clearly an agenda of operations research and network science. And from the financial perspective, questions that remain unanswered is how do you compare the different asset prices over such networks when you consider that we might have different choices of nodes that are part of clearing arrangements, different choices of edges. There's also the capitalization of central counterparty clearinghouses. So those would be additional cushions or capacities at the nodes. Cash that comes from various sources. So that would be a way by which cash is transferred from various nodes before we clear the network. and of course the most important question, and here there's this whole topic of fair allocation and what would be a fair contribution by members that are heterogeneous in risk. So what happens at the network and what are the potential loss? This is used to understand the risk profile of the various members, and then given these various profiles, what would be fair contributions to the capitalization structure of the clearinghouse. There is a trade-off, as we have seen. There is, of course, if we put everybody in a clearing arrangement, there would be no seniority loss, but this may not be feasible because different counterparties have different risk profiles. So in my opinion, one of the open questions is how do we realize the potential of decentralization of multilateral netting and portfolio compression? Can this be done automatically? And in general, decentralized solutions are very are using a lot of collateral. So collateral is posted, but there is in general excessive collateralization. So the real question is how do you design decentralized clearing system that balance this counterparty risk and balance excessive collateralization? Okay, so thank you very much. That's okay.